Contrast with Frank. So this is our last unit of the series. So Brian Swingle from Maryland will tell us about relations between quantum information and gravity.
Okay, thanks for the invitation to come. Excited to be here. I was a student at the Boulder Summer School 8 years ago, so this is an indication of what you can become if you pursue this as a life choice. The title on, can everyone hear me? Good. The title that was given to me was something about quantum many-body physics and gravity. I changed it to quantum information scrambling, but I will talk about gravity tomorrow, quantum gravity, in the second lecture. The other thing to know is I have written some lecture notes that you can find at this old website of mine. There's the address, physicsmonkey/qscrambling. In addition to those notes, I have a couple of links there to some reviews on ADS-CFT. That'll be for tomorrow. If you just want to look at one of those, I would suggest looking at Mark van Ramsdonk's lecture notes on entanglement and gravity. That will give you some flavor of what we'll talk about a little bit tomorrow. Okay, and the lecture notes are still in progress. They'll appear on the archive eventually. So if you see an issue or something, shoot me an email. There's my address, and if I'll acknowledge you when you help me fix it. Okay. So what I'm going to talk about is information scrambling in actually local quantum many-body systems, and with a special focus on strongly interacting systems and also quantum gravity. So I'll explain. I won't assume you know anything about quantum gravity, and I'll sort of explain a little bit about it in a sort of ADS-CFT crash course next lecture. The goal is going to be to understand how to quantify precisely the spreading of information in a quantum many-body system, and also how this relates to the emergence of causality, notions of causality in complex systems. Okay, and I'm going to talk about things like entanglement spreading, out-of-time order correlators, butterfly velocity, bounds on information propagation, and these kind of topics. All right. So broadly speaking, the things I'm going to discuss here arise when asking questions like how information spreads across a system, are there fundamental bounds in quantum dynamics, how does locality emerge in quantum gravity? These are the kind of questions, big picture questions we're interested in. It may not be obvious to you that these questions are related, but hopefully by the end you'll have some sense of how they are related. And like I said, I'm going to focus on strongly interacting systems not because weakly interacting aren't important, but it's better understood there how to characterize the propagation of information, because you have waves or particles that move more or less freely around, and that's like electromagnetism. We sort of understand how to communicate with radio waves and whatnot. Sort of my goal in these lectures, more precisely, is to sort of explain to you how exactly you can quantify information spreading, and how this is related to the emergence of causality. And the idea is going to be that commutators of local operators, local Heisenberg operators, is going to be the right way to quantify information spreading. And so this is kind of connects to a series of developments that have been taking place recently in the quantum chaos literature, things like out-of-time order correlation functions, black holes in the butterfly effect, all this kind of stuff. So we'll touch on that, and I'll explain to you what these things are and what they have to do with information scrambling. And in particular, I think from my perspective, there's a little bit of lack of clarity in the field about what exactly these OTOCs are doing and what they're telling you in a local system. So I'm going to try to construct a physicist's proof of the fact that they measure information scrambling. Okay. And that they measure information propagation, and again, explain to you what those things mean more precisely. The first lecture today will sort of introduce all the ideas and work in the context of a lattice model to try to give you a very concrete setting in which you can make everything very precise. And at the end of the lecture, I'll try to argue that something called the butterfly velocity, which you obtain from out-of-time order correlators, actually does indeed precisely quantify how information spreads. In the lecture tomorrow, I'll kind of repeat the story, but now in the context of quantum gravity. And you'll see how everything carries over in a very analogous way, and that this butterfly velocity, information propagation velocity, has a very physical meaning in quantum gravity. It's related to the fact that you have to have some kind of emergent notion of causality in a gravitational system, and that causality will come from limitations on information propagation. And then in the final lecture, I'll tell you about a sort of more microscopic perspective on this physics, the physics of operator growth, and I'll explain to you a recent conjecture that we made about the universal structure of operator growth in chaotic systems. Okay, so that's kind of the plan. So let's start out with, and of course ask questions at all times. Let's start out with the basic problem of information propagation. What do we mean by this? So let's imagine we have some lattice system with a bunch of sites, just for simplicity. And we have a Hamiltonian, which is a sum over the different sites of some local operator little h sub r. And I'll give you an example of this later on, but just think of this as something that, these sites are each spin a half degree of freedom, and this little h of r just couples a few nearest neighbor spins together. And I sum over all different positions in the lattice, so this is the direction r. Okay. And, okay, so we know that this some Hamiltonian, it will evolve quantum states in time. And typically, because these interactions couple neighboring sites, something which is localized here will spread over the system as you evolve in time. So we want to understand that spreading and how to precisely quantify it for the case of information. You may be more familiar with this problem in the case of a conserved charge, like electric charge or energy. In that case, typically you find diffusive behavior. So if you put some localized charge, the charge will spread diffusively throughout the system. But for information, it's not so clear what one means. Okay. So what I want to do is introduce the idea with a sort of thought experiment where I have two parties, one called Alice, another party called Bob. And let's imagine that Alice and Bob each control a region, here A and here B, of this quantum mini-body system. And what Alice wants to do is she wants to send a bit, A, to Bob. So Alice will send this bit A, and Bob wants to get B equals A out. Okay, that's the goal. So in other words, Alice just wants to send some information to Bob using this shared physical resource of this system in some particular initial state, right? So, okay, we sort of know how to do this. Suppose the system included electromagnetism within it, then, well, Alice could make some kind of electromagnetic wave locally, which was tailored to move over to Bob. And then, depending on, Alice could choose two different kinds of waves or different polarizations or something. And then when the wave gets to Bob, Bob can measure the wave and extract the bit that Alice wanted to send. Okay. So more generically, more abstractly, we can imagine that Alice, should I write down here or is it too low?
You can also push up the board.
I can also push up. I just don't want to erase my, I'll go over here. So Alice, depending on A, can apply some unitary UA to the state. Let me write it this way. A sequence of operations. Protocol. Alice applies UA, so some unitary, which depends on the bit she wants to send, right? If she wants to send 0, she makes a wave of one type. If she wants to send 1, she makes a wave of another type. System evolves. For time t. So this is the wave moving across from Alice to Bob, ideally. And then maybe Bob measures some observable m sub b, and depending on the value of b that he gets out, he says Alice sent him either 0 or 1. Right? So this is a just very standard setup. So let's track what happens. Here's the quantum state. Over here, well, let's say the system begins in some initial state psi. Then after Alice applies A, the system is in state UA times psi, like that. Then the system evolves for some time t. So that corresponds to time evolving after Alice has applied the thing. And then at the end, after this time t, Bob measures, right? So the probability that Bob measures B, given that Alice did A, is just the expectation value of MB in this state. Okay.
So you want to think of MB like B is equal 0, 1, and it's a resolution of the identity?
Yeah, roughly. I'll actually comment on that in just a second. So any questions about this besides the question that was just asked? Any other questions about this basic setup?
Okay, so UA encodes this A?
Yeah, the little bit, right. Like Alice makes a wave of frequency 500 megahertz or a wave of frequency 10,000 megahertz or whatever and sends them to Bob, and then Bob measures the frequency.
What if there were no what would it mean?
Yeah, so good. So this comes to the question we just asked. One thing we want is if Alice does nothing, then Bob should not get either outcome. So if you like, Bob should have a third possibility, which I'll just call null. That is no signal. And then I could think of there being a measurement operator associated with this, such that the measurement of null plus the measurement of 0 plus the measurement of 1 is the identity. Right? So Bob gets one of these three things. Mathematically, what it means is that the expectation value in state psi this should be equal to 0 when B is 0 or 1. Right? That is, if Alice does nothing, then Bob's detector, which either says no signal or Alice sent bit 0, Alice sent bit 1, should just give 0. That means all the weight is on Alice or sent no message.
So we can also think of this she's trying to send a trip at one of the encoders.
Yeah. And so using this fact here, one can show by inserting UA dagger right here to the left-hand side of this thing that this probability of B given A is actually the expectation value really a matrix element of a commutator between the operation that Alice does and the measurement that Bob makes evolved in time for time t. So here MB MB of t is the Heisenberg operator. Like this. And so what it says is, in order for Bob to get a signal, given that Alice did something, it had better be that the measurement that Bob makes in Heisenberg form does not commute with the operation that Alice did. Right? If you're familiar with the theory of linear response, this kind of makes sense. Linear response is about the commutator of two operators, and it says that it tells you when some observable A responds to a perturbation B that happened sometime in the past. It's about causality. Sorry?
Is this missing something entirely? It's not an expectation value.
I think it's right. Sorry, what's missing? No, this is right. It's this thing. Right, you see that the first term is UA dagger MB UA. That's our physical result here. And the second term, I have the UA and MB reversed. That gives me the UA dagger UA. That dies, and I get this condition. So I just added 0 to my expression for free and wrote it in this commutator form. Other questions about this thing?
Can you say something about psi? Like, so how is psi? Both Bob and Alice have access to psi.
Yes, but only local access. So psi can be some highly entangled state. It can have correlations, like from one side to the other side of the universe. Yeah, the system can be large.
Between Bob and
Yeah, a system is the whole thing, right? So the system can go on. You can have a big world. There's some initial psi, which can be whatever you want. Nevertheless, this shows that if this commutator vanishes, then there's no way to send a signal. Other questions?
If it vanished completely, wouldn't that sort of be like sending a perfect signal because you just switch them? So B is the opposite of A.
B is the opposite of A. So I guess that, yeah, the thing is, I think if I understand your question correctly, the problem is there's a third setting, which is that nothing happens. And that's what that's what Bob actually concludes if this thing vanishes, just that he didn't get anything from Alice.
But if you took his probability, I think that's the point of the question.
Yeah, the probability for Bob to get the message, to get 0 or 1, is 0. But Bob actually just gets null with probability 1 if Alice did nothing.
Can you say a little more about this sort of Alice didn't do anything, so Bob has a clear outcome that you desire? Because it seems like she's going to be able to sort of, this condition would let her message by not doing anything. Is there an important role for this no outcome? Or can you do this by talking about the attempting to send a single bit?
I think you can just say it like, I mean, let's see. Yeah, I mean, I think if Bob sees nothing, it doesn't tell him, it just tells him, it doesn't tell him anything, right? If Bob sees null, it just means, like, maybe his state is changing in time in some way, but it's not correlated with the information that Alice wanted to send, right?
But she's sending it, like, when I don't call my parents on Sunday, it means everything's okay.
Yeah.
In the same way, it seems she can send information here, so I'm just worried about that.
Well, I guess you had to pre-agree on something like that, right? I mean,
As do they.
yeah, as do they. So if you didn't have this, like, if you didn't do this null thing, then it would just say the probability was independent of what Alice did. So it's like a channel where nothing, Alice puts in A. So this is another way of saying it would be Alice puts in A, and then what Bob sees is independent of A. So then that's another sense in which you're not sending any information. Okay, other questions? Yeah.
The term that you added is 0.
Yeah, it's just 0. It's just 0. It just says in this setup that if Alice does not send a signal, then Bob doesn't.
You have to take a particular step to satisfy a particular method.
Well, yeah. There's some, there's some choice there. But if you like, as I was answering to Grant, if you like this different setup, make M0 plus M1 identity, and then what happens is just that M0, the outcome, is independent of what Alice did. So in like Shannon theory, that means that the mutual information is 0, so the channel capacity is 0, so you're not transmitting any information. So the idea, what I hope this little thought experiment convinced you of, is that commutators of local operators tell you about information propagation. I still didn't define exactly what I mean by information propagation, but at least it should be intuitive from this point of view that there's something going on here.
Can I just ask a
Yeah.
question? I'm still confused about this condition upper right.
Yeah.
0. It seems like that's just a matrix element and it's some value. Maybe that's, you subtract it off and then you get 0 if there's no signal. But, that's just a matrix element of null with
Yes.
of the evolution operator with psi.
Yeah, I mean, I think what maybe this is not the right way to say it, but I just have in mind that the case where Alice can send a wave or not send a wave. And if Bob doesn't see a wave, that's what this means.
Right. I mean, like if that's not 0,
Yeah.
the rest still makes sense. Like that's just some magnitude squared of the matrix element between psi
Yeah.
and h, between psi and the null state.
Yeah.
And then you're subtracting that off. So relative to that,
Yes.
if the signal is different, then
Yeah. Yeah, like in this 0-1 setting where there's no null, there's just, you either have, you either send 0 or 1. There's no third setting. Then what it means is just that Bob's measurement is independent of what Alice did. So so this expectation value can be non-zero,
yeah, I think
and it can be something. It just doesn't matter what Alice did. That's the crucial thing. So that in that sense, no information has been sent. Bob can't figure out anything about what Alice did or didn't do. Okay. Yeah. So given this, the thing I want to talk about next is the behavior of these commutators. So what can we expect from these things? Now, probably it won't surprise you to learn that commutators of local operators can have lots of different behaviors. Yeah.
So this seems like a protocol for transporting like a classical bit.
Yeah.
Is it fundamentally limited to that?
No.
So you could transfer like a qubit or similar.
Yeah, just imagine like a photon where you've imposed, where you put the information in the polarization, say, or you're sending an atom in hyperfine levels in some superposition. That's perfectly fine. So the first question we can ask is, given that these commutators could have lots of different behaviors, maybe the system is chaotic or integrable, interacting, non-interacting, localized, delocalized, lots of different possibilities. First thing you might want to know is, are there any fundamental limits on these objects? Okay. Well, you're probably familiar with one of them, which is the speed of light limitation. There's something called microcausality. In quantum field theory, which says that if you have some operator v of x at space-time point x and some other operator v of y, then the commutator between the two of them is equal to 0 exactly as an operator statement if x and y are space-like, separated. So that's a bit of jargon. What it means is that if you start from, here's one time slice, t equals 0, t, if this is x, where operator w is located, you draw a light cone, light zero light rays, and if y is over here outside of the light cone of x, then the commutator exactly vanishes. Right, so that instantiates this idea that in a relativistic quantum field theory, absolutely nothing can happen outside of the light cone. That is, it's not just hard to send information in the sense that this commutator is small, it's just absolutely zero as an operator. So the speed of light provides one fundamental limit on information propagation. Right? Speed of light. Now another limitation you may be aware of, you may have heard about, is called a Lieb-Robinson bound. That applies in the context of lattice models. Frank mentioned them this morning. I think Andrew is going to talk about them this afternoon if you're interested. And the first appendix of my notes contains a very simple example of them for you to look at if you wish. There the idea is in some lattice model of a reasonable type, say of the type that we discussed over here, where I have some local interactions in which the local Hilbert space is finite dimensional and the norm of these operators is also bounded, so they're finite norm operators. You have something like this. You have a picture of x, some other kind of cone. Now this is the slope is what's called the Lieb-Robinson velocity, v sub LR. And you have a statement like this, that the operator norm of w of x and t, v of y, the commutator, is less than or equal to some constant times the norm of w, the norm of v, e to the a t minus b x minus y, like that. So let's process this for a second. So this is first of all the operator norm, so it means it sort of upper bounds any possible matrix element you could care about, right? So it's a very strong statement. And over here you see the operator norm of w and v that has to be there just to account for making w and v large. You multiply them by a constant, you make the operator norm bigger, but that shouldn't matter. So we just divide that out. And the physics is this term, which has an exponentially growing in time piece and an exponentially decaying in space piece. And here, the Lieb-Robinson velocity would be a over b. So that you could rewrite this as c w v e to the t, sorry, e to the a t minus, like that. So what this means is that if the separation between the operators, it's much larger than t times the Lieb-Robinson velocity, then this thing in the exponent is very negative, and so the operator norm is small, right? So they approximately commute as operators. So you don't have this exactly vanishing statement, but you have within at least exponentially good approximation that the operators are small, right? So I just, it's just sort of notation. Think about this w operator is expanding to live in this whole region here. And then as a function of where I put the v operator on this line, it either commutes or does not commute depending on whether it's inside or outside that region.
So you could write equally well v y t or something? Or?
Well, v y t prime, and then what matters is the relative time difference. Because if they're at the same time, then they're the same unitary. And then they either commute or don't commute depending on what they did at time 0.
Oh, then it's rather v of y0, right?
Yes, that's right, yeah. You should think of this as being y at time 0.
So what would eventually you get a tail? Like if you're in the lattice model with no, like a single band,
Yeah.
then you have just, there's still a maximum velocity where, you know, basically the pi over a divided by the bandwidth, or bandwidth divided by pi over a.
Yeah.
So where are these higher velocities coming from?
Well, I mean, so there's
I know it's not relativistic, but it's there's still kind of an ultimate, you know, bound in the velocity of anything.
there's two things to say, right? Like, so first of all, this is a bound that you prove without knowing anything about the Hamiltonian. So it can always be the case that for a particular system you know more.
Okay.
In your case, the commutator, say, of two creation operators, right, would look like this. Where Ek is the energy of this state. So you could try to look at this integral in saddle point, in which case if the ratio of x over t is within the energy, the velocity window, then there's a good saddle point and you get essentially strong propagation. If it's outside, then there's no good saddle point. There's no saddle point solution, but it does not identically zero. It still decays. So it's like an evanescent wave or something like that. Yeah.
The constant c depends on A and B. So is there really one definite velocity, or is there really a family velocity?
Well, so the Lee-Robinson velocity depends on your strength as a mathematical prover. So people often say the Lee-Robinson velocity, but there are different estimates that you can make, different like approximations and so forth. So it's really like it's a procedure which gives you an upper bound. It may not be a tight upper bound, and these various constants can depend on how you choose to bound things, right? So I don't think of there being one Lee-Robinson velocity for a system. It's like you can prove an upper bound, which may not be tight. Yeah.
We didn't assume a linear cone so that we have a constant velocity. Can we imagine like other kind of cones, like so that we have a series of Lee-Robinson bounds?
Good question. So here actually we didn't assume a linear cone. This actually comes out of the argument. But it could be the case in a given physical system that the information propagates more slowly than that. Maybe with a velocity that's slower than this Lee-Robinson velocity, or maybe even not ballistically. For example, if you have non-interacting fermions and you place them in a disordered potential, so there's like a local potential which varies in space, then in 2 and 1 dimension they're completely localized. They don't propagate at all. In 3 dimensions you can be in a phase where they propagate but diffusively. So they typically move away from their origin by an amount square root of time. That's diffusion. So the Lee-Robinson bound in that case would be very loose. Yeah, Frank.
Well, actually, cases known where the Lee-Robinson velocity is not equal to the maximum group velocity of your single particle excitations.
Well, I don't know what you mean by single particle excitation in general.
If you have like your dispersion relations.
Well, I don't know what you mean by dispersion relation. Right. Suppose there's no like weak interacting limit. I mean, yeah, I guess so. You're saying let's take, for example, a gapped chain. So there's always going to be, with translation invariants, say there's always going to be some like low-lying mode that disperses, and that has a velocity.
So the question is, are these always the
That's a good question. I don't know.
fastest modes?
I'm not sure if you can say that. It's a good question. Okay. Other questions? So, but now I want to make an important physics point. Just like the speed of light is not relevant speed limitation for most of us in our daily lives, it may be that also the Lee-Robinson velocity in a lattice model is not really relevant as a speed limit for the system that you care about, at the temperature you care about or the energy density you care about. It could be that there's much slower speed limit, which bounds nevertheless all the interesting things you care about, but which depends on the state and the physics of the problem. Right? And so what we're going to sort of be investigating in the rest of this course, this lecture course, is really how these kind of low energy, state dependent, physical system dependent propagation velocities arise, how to characterize them, how to think about them, and what they mean physically. Okay, so to do that, let me consider a concrete model now. Model is one-dimensional. Everything is going to be one-dimensional. Much of what I'll say can generalize to higher dimension, but for the sake of pictures and simplicity, I'll focus on one dimension. This is called the mixed field Ising model. It consists of three terms. The Hilbert space is a single spin a half per site. And the Hamiltonian consists of three kinds of terms. The first term is a nearest neighbor interaction, which assigns low energy to states that are aligned in the z basis. The second term is a term which wants the spins to polarize in the plus z direction. And the third term is a term which wants the spins to polarize in a plus x direction. And because x and z don't commute, we often say that the sigma x term generates quantum fluctuations in the z basis. That is, it causes transitions between different z eigenstates. So this is a sort of non-trivial interacting quantum Hamiltonian. It's also conventional to set j equal to 1, which just means we measure all energies in times and units of j, or 1 over j, as appropriate. And then there are two parameters. There's hz, which is the magnetic field in the z direction, and hx, which is the magnetic field in the x direction. Now, there's a lot to say about this Hamiltonian. It's a very well-studied Hamiltonian. In particular, when hz is equal to 0, you'll find that this system is equivalent to free fermions. And in that case, you have this kind of free particle wave picture that we discussed before, where information can propagate very easily just by exciting a fermionic particle and sending it on its way somewhere in a wave packet. However, when hz is not equal to 0, for generic values of these couplings, this model is actually quantum chaotic, non-integrable. It thermalizes. And so we'll study that case. A consequence of thermalization is that expectation values of local operators in some state psi, such an operator like this, so such an expectation like this, like we saw over there, this typically decays rapidly in time. What does that mean? In a single particle setting, this kind of commutator would be like the propagator for a particle to move from point x to point y after some time t. So if you make a well-defined wave packet and that wave packet moves, then this will remain large out to very long time. It only goes down because the wave packet spreads. But in a strongly interacting chaotic system, these quantities will typically decay because of thermalization. The physics of thermalization, or one aspect of the physics of thermalization, is the system loses memory with initial condition. You can't remember where you came from. All you see is this generic thermal state after a short period of time. And precisely because these kind of commutators measure linear response, they tell you what happens to some observable when you ping the system with something else in the past, they would have to be small in order for thermalization to happen. Right? So a consequence of thermalization is that these kind of commutators would be small. And so in particular, if you're looking to try to do this experiment that Alice and Bob are trying to do, Alice can excite some strong wave initially, some excitation, but as that wave moves, it gets weaker and weaker and weaker, so that by the time Bob sees the wave, in quotes, because he doesn't see anything, there's nothing happening, right? So in other words, unless Alice and Bob are within a short distance of each other, they can't communicate. And this is not surprising. If you want to send a signal to someone else, you don't place yourself into the quark-gluon plasma. That's a bad idea because that causes everything to go crazy. You sit in vacuum and send signals with electromagnetic waves because they're weakly interacting and propagate for long distances. So it sort of looks as if nothing is moving anymore in some sense. But of course that can't really physically be right. Things are still expanding. But these expectation values of commutators no longer seem to give us the physics that we're looking for. They don't seem to be good measures of information spreading. And you can put this system on a computer for 20 or whatever spins you want. Well, not whatever you want, but for 20 spins. And you can calculate this object and just see it decays. So what I want to cook up is a new thought experiment that even in this strongly interacting chaotic quantum many-body system will still show us that something is spreading, that information is spreading, that quantum information is spreading. Yeah.
I should not think about like Alice sending a wave packet with definite momentum or something, right? Like not.
You can think about that.
Okay, it will change how it. I guess how what I measure decays because it's different than just diffusing, right?
Yeah, it would move with some speed, but its amplitude would get small very quickly. Right. And even, of course, total momentum is conserved, so the system itself still has that momentum, but the momentum is distributed amongst all kinds of inaccessible degrees of freedom that you can't easily probe with a local operator. Yeah.
Can you relate it to your comments about the Robertson bounds? I mean, so there's no decay. There's just if you within the cone, then it's.
Yeah. So here within the cone, Lee Robinson allows the commutator as an operator to be large. What this says is that matrix elements of it, diagonal matrix elements, are small. And in particular, this is just the expectation value, but I could generalize this to like make some local perturbation, like this signaling protocol, in which case you would find that matrix elements of the commutator between states that are related by simple operators is small. That doesn't mean the commutator itself is small as an operator, but these matrix elements are small. Yeah?
The statements you made about this model, are they state dependent, or again, it's about operators?
I'm really going to focus on the operator later, but yeah, this model, I mean, it's hard to say in a thermodynamic limit because we don't really know what happens, but like if you do finite size calculation, you will see the difference. Like the states that are all plus y states thermalize very well. The states that are like all plus z or all plus x don't do as good of a job, presumably because they're farther out in the spectrum. The plus y's are right in the middle of the spectrum, so they have the most sort of thermalization ability. Whereas these other states are sort of closer to the ground state or the highest energy state. And so in small size system, it's harder to see them. I mean, they do still exhibit the phenomena, but not as dramatic. Presumably an infinite size system, it would not matter.
Is it possible to make a connection between the statement that this decays rapidly in time and the earlier different commutator we looked at? With this thought experiment with Alice and Bob and the unitaries?
Yeah. So just imagine that just do the same thought experiment. Alice like pings the system with something, and then Bob tries to measure something else. And what this will tell you, then you have some matrix element of this commutator, or alternatively, you insert some other operator here. That's a matrix element of the commutator between two different states.
And that typically decays?
That will also typically decay. You would need, so basically the statement that we believe physically is if you take some kind of reasonable state here, like a uniform state, and you make another state which is acting on that original one by some small number of local operators, then the matrix element will be small. So in other words, you do some local things, you add some particles, you excite some energy at different points. That won't last long from this point of view.
But in this model, there are sort of big, complicated states that
Yes, something is still spreading in a very definite way, as I'll now show you. Okay? So let's consider a different thought experiment where what we do is the following. We take our infinite system and right here at the origin, or some arbitrary point, we put one extra qubit, which I'll call the reference qubit. This reference qubit doesn't participate in the dynamics, so just think of it as being in an isolated box. But before I isolate, I'm going to entangle it in some way with the system. So more precisely, think of there being two states, state psi1 of the system and state psi2 of the system. And I prepare a state like this of the combined system plus reference, where I've entangled the system with the reference, right? And let's think of these psi1 and psi2 are orthogonal, so actually this is a maximally entangled state between the system and the reference. And let's further think that these states psi1 and psi2 differ only locally. So there's some little region here, A, where the states are the same everywhere outside of A, but differ within A. So for example, in that model, a very nice choice would be to take something like this. Psi1 is all plus y, psi2 is minus y on one site and then plus y everywhere else. So I'm creating entanglement between my reference and the system at one localized position. And then what I'm going to do is I'm going to let the system evolve in time. And I'm going to try to study where that entanglement moves to, how it moves in the system. And the quantity I'll use to do that is the mutual information of the reference with a region A. So I'm assuming surely you've seen mutual informations. If not, well, sorry. These are entropies of the reference and the system, the region A, minus the entropy of the combined RA, right? And the idea is that at initial time, if A is, say, this little region right around where you locally entangled the system, then the mutual information between R and A is 2. That's the biggest value it can be, and it just says that R and A are maximally entangled. So now what I'd like to do is study this mutual information as a function of time and a function of the size of region A. So at t equals 0, mutual information between R and A is 2. The mutual information between R and a complement of A is 0.
When you say 2, you mean 2 log 2?
Yeah, I'm actually using base 2 log here. I'm sorry. No matter which one you use, someone's going to be mad at you. So actually, I use both in the notes for maximal confusion. Okay. This little c means complement means all the rest of the region besides A. Yeah.
In the state psi1 second defined, can you say what is A and R?
Good. Thank you. So here, this would be A. this would be a complement. That make sense? Huh? Oh, this is just psi 1 and psi 2, so R is over here. I'm just telling you that these are the system states. So the full state,
It's like if it's spin off, then it's
yeah, so just think of it, I have a bell pair between a reference and site 1, and then all the rest of the sites are in plus y state. Does that make sense? So bell pair between R site 1, all other sites are in plus y.
So both R and A are just single splits.
That's right.
but they're also like, doesn't matter that, like you can take 0R to be plus y and 1R to be minus y, or
So 0.
what is 0R?
Yeah. Sorry, I'm using this quant information. Yeah, so think 0R is plus y and 1R is minus y.
But it doesn't really matter.
Yeah.
As long as they have,
They're just orthogonal states, so they're related by unitary on R, so it doesn't actually matter what we call them. So remember the rule is like R doesn't evolve. So we have a picture like this. I initially entangle R in site 1, say, and I put the other sites in some initial state like this. Think of this as a matrix product state that Frank told you about. And then I evolve in time, for time t, and nothing happens to the reference. This is for an n-spin system. So is the setup of the experiment, the thought experiment, clear? Any other questions? So now I'd like to show you what it looks like. In the notes, there is an actual calculation. I can give you the MATLAB file if you want, where I actually just compute this for that model with certain parameter choices. This is what the curve looks like. Let's see, how should I do this? I'll draw it here and then send it up. So I want to compute the mutual information between the reference and a region of size from 1 to x as a function of time. This is 2. That's 0. And I'll show you different curves. So for the first curve, for the first site, what happens is it starts at 2, and it drops very rapidly down to 0. So the mutual information begins at 2, but then drops rapidly as a function of time. This is the size, right? So this is this thing as a function of time. So this is the interval 1 to 1.
it's the size of the age.
Yeah, it's the size of the region I'm looking at the entanglement of the reference with. So this is just the first site. Now if I look at the second site, I look at the first 2, 1 and 2, then what you'll find is that it remains close to 2 for a while, but then eventually drops down to 0. Actually, it's more like that. So this is the first 2 sites. If I had the first 3 sites, then it remains non-zero longer and then drops down. So you'll forgive my bad drawing, but what this is supposed to show you is that these curves here, if you look at the data, are expanding out ballistically. And what that tells you physically is that at time 0, the entanglement is all between the first site and the reference. But pretty quickly, that entanglement goes away. The first site becomes unaware of what's happening on the reference. But the first 2 sites still know. But then after a while, that also starts to decay. they start to lose understanding of what's happening with the reference, but the first 3 sites still know, and so on. But then that decays, and the first 4 know, and so forth. And this separation here, this sort of time to start turning down, is actually growing linearly with time, with x. So in other words, it looks as if the entanglement is initially on the first site, then within the first 2, then the first 3, then the first 4, but it keeps expanding. You can't stop it. It keeps getting bigger and bigger and bigger, so that at late time, for any fixed set of sites, there's no entanglement between the system and the reference. Yeah?
So in this case, is A equal to 1, 1? What's your A?
I'm sort of varying A. Right, this is for different choices of A.
Okay, so A is a...
So think about this is like A.
Can you say, so if you're, let's say you have a pure state, so SRA is 0?
If R and A are combined together pure, then yes, SRA is 0.
Oh, I'm sorry, but A...
But here A, I mean, it doesn't have to be. The point is, basically the point is, A can have entropy. It's just that the excess that comes from the entanglement is like totally accounted for sort of within A. That's the physical interpretation. Yeah?
If I took that commutator in the beginning and then take integral or something with respect to x, would I get something similar?
No, it actually still decay. If you take integral with respect to x, no, it will still decay, I think. So at late time, yeah, like these curves here would actually start going down earlier. It wouldn't be ballistic. Because no matter which x you choose, they're small. Like say they're decaying exponentially with time. So it could be something like the size of the region times e to the minus t, but that's going to decrease from time 0 instead of having this sort of onset behavior.
Yeah, and they wouldn't sum up to something.
Yeah, they wouldn't sum up to something nice.
If the boundary is open, what will happen?
Actually, what I showed you is for the open boundary. So if it's infinite, just like to make it a radius around the thing.
It doesn't reflect off the boundary and boundaries.
Yeah, in this in a weakly interacting system, it would reflect or something, but in the strongly interacting case, there's not really any kind of reflection to speak of, at least in these observables. Yeah.
So you gave a picture where the kind of pulsation of information is expanding, but it could also just be like a soliton moving.
Yeah. That's true. It could be like that. But you can check. I mean, I didn't show in the notes or here, but you can check. Like you can look for clusters that move, and they'll all be 0 at long time. So it's not just like a wave packet propagating. No, here I meant the complement without.
So like when you write SA, how is that defined? Like you trace over R?
That's just the entropy of A. You trace over R and the rest of the system.
And the AC.
And the complement of A in the system, yeah. Okay, so how can we, so something's clearly spreading here. Information entanglement is spreading. Can we relate this to commutators in some way? That was what I tried to motivate at the beginning. The commutator tells you about information spreading. But we saw that these matrix elements or commutators were small, so that's not going to cut it. But the next simplest thing you might think of, which sort of mimics the operator norm to some extent, would be to look at the square of the commutator, the absolute value of it. That would be sort of the next natural object, the variance, instead of the average. So to that end, what does this have to do with commutators? if anything. Well, so the idea is let's look at what I'll call the squared commutator. Which is the expectation value in some state psi of the commutator of a local operator W with some other local operator V. Let me write this a little bit lower. Just erase this. So commutator of local operator W at position X and time T with other local operator V at position Y and time 0. Dagger, that's going to make it positive. The same thing. So if you stare at the subject for a minute, you'll see what I have here is some operator and some operator dagger. So the thing I'm taking the expectation value of is positive definite. And in particular, it can't have the kind of phase cancellations that led to the vanishing of the expectation value. So this can't possibly be 0 unless the operator itself is 0 in some precise sense. Or at least its overlap with this state is 0. Right? And so what does this look like? Well, you can also calculate this quantity for, say, local operators in this model. And what you'll find is a function of the separation. Let's suppose it's translation invariant. Assume translation invariance. This implies that C of x, y, t is just C of r equals x minus y, t. Then what you'll find is that, okay, for r finite and t 0, the operators are separated in space, so they initially commute. So the commutator is 0. But as a function of time, this operator W is expanding. It's becoming more complicated. And what you actually find is that as a function of, say, position, there's a special position at a given time. This is at fixed time. The commutator will be some value, which is sort of maximal, and then it will drop to 0 outside, right? So think about there being some kind of expanding radius of non-commutativity. There's a velocity called the butterfly velocity because of connections to chaos, which is denoted V sub B. And so at a certain time, if you look at this squared commutator, inside the butterfly cone, you'll find that it has some large non-zero value, some finite value. Outside of this cone, so outside of VBT, it's small, it's close to 0. This thing, as I said, is called the squared commutator. If W and V are unitaries, this is not essential, but just suppose they were unitaries, like single Pauli operators are unitaries, as well as being Hermitian. If W, V unitary, then C turns out to be 2 minus F star, where F is the by now infamous out-of-time order correlation function. So named because the ordering of the operators in the correlation function jumps from time 0 to time t to time 0 to time t. So this is the so-called out-of-time order correlation function, or OTOC, which has made an appearance in the quantum chaos story. Well, more than an appearance, an epic splash.
I think you're blotting the out there.
Yes, you are right. This happens to me every time. Because these commutators are important, let me, how does this work? No, I'm right. You tried to trick me. If R is within VBT, so if it's evolved for a long time, and you look at nearby operators, then they don't commute. It's fixed time. Good try. I applaud your effort. My curve is correct. Yeah.
Can you say again why this guy can decay but the other one does not?
Well, the thing you're taking the expectation value of is positive definite. And it sums over, think of it as summing over all possible matrix elements of that thing. So while it has to be positive, first of all, because it's a positive definite operator, and I'm summing over all matrix elements, not just simple ones. So somewhere in those complicated states, there'll be things which have non-trivial overlap, and I sum those up, and that's why I get something finite. Alternatively, from this point of view, writing C is 2 minus this out-of-time order correlator. If these operators are all separated in space-time, so one's at time 0, one's at time t, one's at 0, one's at t, then you would expect that kind of correlation function to be small, because in a chaotic system, everything is small when things are separated in space-time. So you would expect f to be small at late time, which would imply that C is 2. Yeah?
Is it possible to see the terminalization timescale in this object as well?
Yes. So, for these unitary cases, a little bit harder, but like if they were Hermitian and not unitary, then there would be another term here, which is time ordered. And what you'd find is that term will have some initial behavior, like it would sort of start out at some non-equilibrium value and then decay a little bit. And the physics is that the time ordered and out of time ordered term behave the same. And then much later on, the out of time order one begins to decay. So the out of time order correlator would indeed, by itself, know about this early time thermalization. It would have some early time behavior, then it would stop changing for a while, and then it would start changing again once this sort of VB time has happened. Yeah.
I have two questions. One, so is it sort of just more important that this thing is almost like counting the number of matrix elements that are appreciable rather than, like in the first case, they decay, but it sort of goes out to more matrix elements, and this is just sort of counting the number of matrix elements that are relevant? And my second question is, it seems more like, obviously it seems more natural to me to consider as like an expectation value of the state, but it seems like the notion of chaos should be like only Hamiltonian dependent. Is there a way to separate those?
So in response to your first question, I would say something like mathematically it's true that you're sort of summing up all these different states, and that's why from a certain point of view it can be non-zero. But physically, I think it's more like the intuition is this connection to chaos, like that in a chaotic system, if you took the semi-classical limit, these commutators would become Poisson brackets, and that would actually measure the butterfly effect. Basically, it would be the time that the change in the position at some late time due to a change in the position at some early time. That's the butterfly effect. So you basically get something which grows with time, like a Lyapunov exponent, exponentially. However, even in classical chaos, the Lyapunov exponent can depend on where you are in phase space. Right, can depend on the energy shell you're sitting at, or even the precise initial condition. So I think it's certainly very reasonable that you could have a dependence on the initial state in this kind of questions. And indeed, we'll talk about next time. The idea is this butterfly velocity, to come to the point, this butterfly velocity will function like a speed limit, an effective speed limit for states related to psi by simple operators. So think about psi as like some low energy state, and that low energy state has an effective propagation velocity of information which is much less than the microscopic bound. And we'll see next time actually there are examples where this VB is arbitrarily slower than the microscopic speed limit. So really physically, the physics is that something is moving much more slowly in your system, in the same way that strong interactions might, for example, cause you to have trouble moving through a room of people because you're hardcore, you have trouble propagating, right? So that can also slow you down very dramatically here. Yeah, Graham.
So will it be possible to make a connection between this C and the product square that we talked about before with information transmission?
Yeah, well, so one very direct thing you can say Is it this probability? So yeah. So if this is small, then this probability is small, which means even if there were some states in Hilbert space that had a high velocity, if the state you have access to is not one of those states, then you are limited by the speed of this commutator here.
But if it's big, it tells us sort of no.
Yeah. Yeah. Okay. So I have like 15 minutes left. So so from entanglement growth, entanglement spreading, we got a velocity vi, right, which is the rate at which these mutual information curves, if you increase the distance by d, then the time it takes for it to decay is d divided by this information velocity. And we have the squared commutator velocity. Give us a velocity which is the butterfly velocity. And what I'd like to claim for you is that VB is equal VI, at least for a large class of interacting quantum many-body systems. So, in other words, the squared commutator provides the right notion, at least for this entanglement spreading protocol, to tell you how the entanglement is growing in space and complexity as you evolve the system forward in time. Yeah?
Is it obvious that both of them should also grow linearly? And did you comment?
I did not. It's not obvious. For this object here, like, let's say that the generic intuition, if you expand this thing out, so this is a Heisenberg operator, which means it's a sum of nested commutators. So if you look at the first non-vanishing term, basically you need to take your local operator and commute it a bunch of times with a Hamiltonian until it spreads all the way to this other point. So the first non-vanishing term there looks like the time to the distance over distance factorial. That's in the notes. You can have a look at it. And if you study that function, you'll find that it becomes order 1 after a time which is linear in the separation between. So just perturbatively, the natural answer is linear growth with time. That doesn't prove that it's true for a generic system, but at least for a chaotic system, we believe that indeed it is linearly propagating velocity. And the same kind of thing can be made for this statement here. So I actually don't know of any thermalizing system where it's not linear in time. The speed can be slow, but it's linear. Examples where it's not linear include non-interacting fermions with disorder and what are called many-body localized phases. In such a state, you'll find that actually the entanglement spreads only logarithmically in time. And these OTOCs also grow, they spread, so this, instead of VBT here, you'd have something like log T. And that's a very much slower growth, but that's because you have some localized state. Yeah. Yeah. So here are the time of initial decay is x over vi. So as I make the size bigger, the time it takes for it to decay grows linearly with x, and 1 over v is the coefficient. Thank you. Yeah?
You said the information is spreading, so is information conserved?
Yes.
So if information is conserved, the quantum correlation is conserved or not?
I'm not sure what you mean by quantum correlation in this context.
Correlation.
Sorry, I'm afraid that does not help me.
For example, entanglement, maybe not entanglement is just a spatial correlation, maybe spatial time correlation in total.
I So one statement you could make is that if you look at the mutual information of R with the whole system, it's always 2, independent of time. So that's a statement of the fact that the entanglement is somewhere. It's not lost.
But the mutual information is only at a fixed time.
Yes.
So it is conserved at a fixed time.
Yeah, so for any time, the mutual information between the reference and the whole system is 2.
I'm wondering whether it's a general statement.
Yes.
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 So we don't need to consider mutual information in time to make it conserved.
I don't know what you mean by mutual information in time, but as a function of time, it's independent of time.
Okay. Thank you.
Yeah. Yeah.
The protocol for the entanglement spreading was independent on states and on operators. So is that obvious that the two velocities, I mean, the butterfly indeed depends on the state as we were commenting.
Yes.
And also on operators sometimes.
Yes.
So is that obvious that they're the same? Does it all?
No, not obvious at all. But there is state dependence here, and that what I put here is an initial state. And for this problem, I assumed it was all plus state, all plus y, which is like an infinite temperature state.
No.
So if I put some other state, if I put a low energy state, then I would, in principle, have a different velocity. So it's not obvious that they're the same, but there is state dependence in that setup as well.
But that one is defined for the infinite temperatures.
No, yeah, sorry. So this VI I think of as in general depending on the state psi. And
So fixing the state,
fixing the initial state,
two velocities are the same.
yeah, that's the claim. And to state clearly in a class of systems for which I believe this is true, like let's say chaotic non-integrable thermalizing systems, then it shouldn't depend on the state even very much, just probably the initial energy density, or maybe the density of other conserved quantities. The only thing which the system knows about at late time is these conserved quantities. So the conjecture would be that, say, in a chaotic system like that Hamiltonian, or like a strongly coupled gauge theory, as we'll discuss next time, these VI and VB depend just on the energy density of the initial state, and they're the same. Other questions?
Are there models where you can prove the conjecture?
So in my notes, I have actually given a quite detailed argument in the appendix in favor of this statement. And in the main text, there is a sort of physicist argument, which I'll try to recapitulate very quickly here.
Are there
Yeah.
models where you can prove the statement?
Yeah, so rigorously prove, I don't think so, not yet. We can certainly, in non-trivial models, check both sides and see that they're the same. I'll show you an example next time. But as far as a rigorous proof, I don't think it's possible yet. Yeah?
So in all this work regarding random unitary circuits and whatnot,
Yes?
VI has no sensible meaning.
No, it does. Yeah. I'll discuss that case on the third lecture. In that case, the V is still meaningful, but what changes is the shape of this commutator.
I mean VI.
Oh, VI. No, that's still meaningful. Why is it not meaningful?
Local random circuits or big random circuits? Local random circuits.
Yeah, it's still meaningful. I mean, so for example, there's a circuit light cone that's always certainly contained in that circuit light cone for any realization of the circuit. So for any realization, if you make A bigger than the circuit light cone, the mutual information will be identically 2. So if you then average over realizations, you're going to get 2. So it does have a meaning there. Yeah.
So following up on Graham's question, I mean, free fermion, like just the Ising model without the Z term, would display this behavior, wouldn't it?
It would or would not?
Would?
Well, yes, it would.
There you can probably prove these.
Well, yeah, okay. Sorry, maybe I was too ungenerous to myself. Yes, for free fermions, we could prove that it's true. Because there, actually, for free fermions, the commutator is actually state independent. And that just follows. You can actually, there's an exercise in the notes to show that for bosons. It's state independent, and so what you just calculate what it is, and then you can use it to upper bound everything else.
The Ising model is integrable, and I always heard that integrable models are not chaotic. So
We need to be careful what we mean by the Ising model. What people sometimes mean is the Ising model without the z field. If I add the z, then it's not integrable, at least for generic values of x and hx and hc.
no, so for when hc is 0, this won't hold.
No, it will. It will. I mean,
Because it's integrable, then it's supposed to be not chaotic.
let me say it this way: the square commutator still provides a bound, but the pictures I drew are all wrong, because, for example, the square commutator doesn't go to 2 at late time; it actually decays back to 0. So after this wave passes, it starts to decay again. So the physics is very different, but the moral story, I guess, that the square commutator provides an upper bound is still true. Yeah.
Is there an example, maybe even just a really simple example, where they're not equal? Or
Where they're not equal. I don't actually necessarily know of one off the top of my head.
not even like a trivial kind of construction?
Yeah, let me think about it, but I don't think that they're. Yeah. So let me make a comment along these lines. So if I replace VB with VLR, say, or the speed of light, then you can rigorously prove that VI is less than or equal to that. And so at least one half of this statement, that VI is less than or equal to VB, is sort of semi-plausible based on the idea that VB replaces the Lieb-Robinson speed or the speed of light as the speed limit. What's less clear and more non-trivial is that the other side of the inequality is true as well. That if, well, I'll actually explain this next time, but I don't have time today. But yeah, it'll turn out that, let's say, I'll say it this way. VB less than or equal to, VB greater than or equal to VI is sort of intuitive, I would say, in the sense that if you replace this with Lee-Robinson, it's a theorem. And if you view this VB as the low energy analog of Lee-Robinson, it's plausible. The other way that VB is less than or equal to VI, that is actually more non-trivial to argue. And I'll actually use something called Hayden Prescott protocol to convince you that it's true. That basically what this says is if you had access to a region which was going smaller than the butterfly velocity, you couldn't recover the entanglement. So you need that whole region to get it back. And the reason is because you couldn't recover it in the complement. And that implies it can't be recovered in the original system. So I'll try to explain that a little bit next time.
Can you just like maybe quickly explain the first one actually? Because Lieb-Robinson to me seems intuitive for like growth of like commutators or both operators and
Yeah.
obvious that like this particle trace and like mutual information is
Yeah.
the local operators.
So here's the physical picture. The idea is, let's imagine t equals 0, t. Let's go back to our light cone picture, like this. Let's say this is, and I'll pick this up tomorrow. Let's call this A complement. Let's call this A sub t, which is just defined to be A expanded by some Vt, where I'm going to call VL the light cone speed, right? So this is just A expanded by t, and then this is AT complement, like that. And so the idea of the argument is that for Lee-Robinson you can prove this, that the time of revolution operator will decompose as a piece here and another piece here, which I'll denote like this. And that the full time evolution is like the sequence of two different unitaries one which acts only on A complement. So that's like this piece here. It takes in information down here and spits some of it out along this light cone direction and some of it out up there. And the other one takes information in here and spits it out up there, right? So the claim is that you can decompose the time evolution operator in this fashion. And if you can do this, then the claim that I made, then this becomes trivial. Because as long as I have access to A of t here, then I can remove this factor in the time evolution just by unitary invariance of the mutual information. And then I simply have the mutual information between my reference and the original state. I've sort of exposed A, the original region, at time 0. And so then the mutual information is trivially 2, right? So this kind of decomposition implies immediately that VI less than or equal to VL. Now to argue what VL, what is VL? Why is VL equal to, say, VB? That argument is roughly like this, and I'll stop after this. Sorry, I know you're hungry. The idea is time evolution operator obeys this differential equation, Schrodinger equation. So let's split H up into a piece which is just in AT, and a piece, let me call it like this, a piece which is the rest. So H equals H AT plus delta H, like that. So there's some Hamiltonian which acts in this region, and then there's something else. And notice that it's well separated from A. It's separated from A by VLT, right? So now if I go to the interaction picture with respect to this thing, then I have U equals e to the minus IH. Let's say t is the final target time. Hat U, so there's a new thing. And this hat U obeys the interaction picture equation like that. So what you have here is your Hamiltonian, which remember is the sum of local operators being evolved in time. And that's what generates the time evolution. So it's sort of plausible that if you know that the commutator of local operators is small, then these terms here are actually themselves small. And so that you could truncate this, which is in principle an operator on the whole Hilbert space. You could truncate it to just live on AC, the complement of A. Like basically these operators start over here, and they kind of race this way. They try to get over to A, over to A, but they can't do it because you have a speed limit. And so you can just truncate sharply here. And then you have U hat being supported non-trivially only on A complement, and you have the desired decomposition. So for Lieb-Robinson or like speed of light, you can prove this rigorously because you can upper bound this thing as an operator. For butterfly velocity, you need to make arguments about the action of this thing on the states you care about. And if acting on those states, it can be restricted to lie in A complement, then you have this decomposition not as an operator statement, but as an operator acting on a certain set of states. So that's why the argument is more non-trivial in that case. Okay, but that's the flavor of the argument for VI less than or equal to, well, this is just a simple result, and then that this should be equal to VB is the non-trivial claim that one makes by analyzing the structure of this time-evolving thing on low energy states. And you need to play games. This is like a sharp decomposition. That's a very high energy thing to do. So it's better to make it a smooth cut between the two. And you can make some arguments and make a heuristic claim that this is true. I don't claim it's a rigorous proof, but it's a strong argument. Okay, so next time I'll explain the other direction a little bit and talk about quantum gravity and how this quantity manifests in that context.